Unit 9, Waves. Now, I know you've investigated waves before at some point in your career of physical science coursework, and I know that you know that one wavelength and one crest and one trough equals one wavelength. And I also know that this symbol is the symbol for wavelength. In addition to all that, basic wave properties come back time and time again to the basic wave speed equation. SWOOF. Wave speed in meters per second, wave frequency in hertz, and wavelength in meters. Most of this unit involves harmonics, which, let me give a long-winded explanation real quick. Yeah, I know that's a little long-winded, but it's the best and most descriptive way I can put what a harmonic is in words and descriptive terms. But you're right, let's get rid of these words and let's look at what a harmonic would be. Let's start with open tube systems. We produce a sound wave using a sine wave generator, as we will in lab, and we produce a sound wave that looks like this in an open tube. If you're thinking about this wave in sheer raw terms of transverse wave, we've gone from the top of a crest to the bottom of a trough. So if you're thinking about how much of a wave is present in a system such as this, and you say, that's not quite going back to the top of the crest, thus completing one wavelength, that seems to me to be 1/2 the wavelength. You'd be right. The length of the tube in this instance is equal to 1/2 the wavelength. Waves are frequently diagrammed as having a standing wave counterpart, especially with sound waves, which is what we work with a lot in this unit. So convention dictates that you have your transverse wave counterpart when diagramming this particular wave. Now we can adjust the length of the tube, and if you adjust the length of the tube a little bit, you really won't hear very much different. So just adjusting the tube a little bit means we just hear just in general the sound wave. If we adjust a little bit more, we just continue to hear just the sound wave. But if we adjust the length of the tube just enough, then what you'll hear is that the sound wave has an exaggerated overtone of itself. As in, the length of the tube is just so. We have a new standing wave produced in which nodes and antinodes for that wave lock in with one another. And you've now generated a new sound, which you can hear audibly by adjusting that length of tube. You have heard the next harmonic in the harmonic series. Numbering these tubes, this would be the first harmonic in that series. The first harmonic is always known as the fundamental frequency for a harmonic system. In an open tube system, we go from first harmonic to second harmonic. The length of the tube for that second harmonic is equal to straight up the wavelength. If you're keeping score of the wave up here on our transverse wave diagram, we've now come from the top of a crest to the bottom of a trough and back up to the top of the next crest. Therefore, in this situation, the length of your tube and the wavelength are equal to one another. If we can somehow stretch that tube even further, we won't hear, so we hear an overtone here, but we won't hear one yet. Still not hearing one. I hear it. So at that new length of the tube, you have encountered your third harmonic. Draw the standing wave generated. And there it is. Draw its standing wave counterpart to keep in convention with descriptions of sound waves. And there that is. This is not a very good wave. I apologize. Hopefully in notes in class I'll draw better waves. In this case, though, if you're keeping score with our transverse wave up here, we've now made our way from the top of a crest to the bottom of a trough, back up to the top of a crest, back down to the bottom of the next trough. If you're keeping track of what's going on. So this is 1/2 of a wave, 2/2 of a wave, 3/2 of a wave. Okay, so the length of the tube is equal to 3/2 of a wavelength. You can see that we've stumbled upon a pattern here that can be heard for 4th, 5th, 6th harmonics and throughout a harmonic series. The equation which summarizes what's going on with open tube system is given as follows. Frequency is equal to the harmonic number times the speed of sound in the air, which is 345 meters per second, divided by 2 times L. This equation is not given as a reference in our AP Physics 1 exam and might need to be memorized by that point. This harmonic number runs from positive integers, therefore acceptable values for h could be 1, 2, 3, 4, 5, or 6, or maybe even beyond. Let's move away from open tube systems and explore closed tube systems. Correction, tube systems which are closed on one end. If we take that same sine wave generator and emit the same tone at the open end of a closed end tube, this is the open end, this is the closed end, we would generate a new wave, and we can adjust the length of the tube until we heard that first overtone, and we would know that we're at the first harmonic or the fundamental frequency for this particular harmonic frequency. At that point, we get a wave that looks like this. Not really much of a wave if you think about it, and our standing wave counterpart. And if you're keeping score with our transverse wave buddy up here, we've made our way all the way from the top of a crest to the line of origin. So we've done that. The length of the tube in this case for our first harmonic or fundamental frequency. Fundamental frequency for closed tube systems, that length of tube is equal to 1/4 times the wavelength. And tube systems which are closed on one end, we skip the even-numbered harmonics and we only experience odd-numbered harmonics. So, as before, we'll lengthen that length of tube, make it longer until we can hear that next harmonic series. Oh, I think I hear it. The next harmonic you hear will be the third harmonic, superimposed as a transverse wave. That'll look like this. See if I can do this with any justice. It's not great, but that's okay. Develop the standing wave counterpart. And there's our third harmonic, opened end and closed end diagrammed. If you're keeping score with our transverse wave up here, we've made our way up to about there. So therefore, the length of tube in this case encompasses 3/4 of the wavelength. We don't even have a full wavelength yet at the third harmonic for the closed on one end tube systems. Alright, fifth harmonic, let's make that tube longer. Let's see if we can hear that fifth harmonic. Oh, I think I hear it. Let's see if we can draw that fifth harmonic. Uh-oh. Ah, yes, there's that fifth harmonic, and I drew it all by myself. Fifth harmonic. In fifth harmonic, the length of the tube is equal to 5/4 of the wavelength. If you notice, we're now able to finally fit one full wavelength in the tube, with 1/4 of the wavelength residual. We can develop, using these rules and patterns, the closed tube equation as follows. Frequency is equal to harmonic number times the speed of sound in the air divided by, instead of 2L, 4L. The other difference we want to draw our attention to is that the harmonic number are only odd numbers if one end of the tube is closed. The final topic addressed in the waves unit would be strings. Strings also produce standing waves and harmonics. Typically in a physics classroom, they're in situations such as this, where we have a string suspended over a pulley, and we have a force of gravity exerting some sort of tension on the string. We would then modulate that tension, force of gravity, wave speed, or frequency value to produce various standing waves in this situation. Let's say that we're able to produce this standing wave in this particular situation. That'd be a pretty low frequency standing wave, and once you get in the lab, you'll see what I mean. In this case, for the standing wave that's produced, we're oscillating up and down. Here's our antinode, node, and node. The length of the string is equal to 1/2 the wavelength. And the next standing wave, the length of the string is equal to the wavelength. And the next standing wave, the length of the string is equal to, you guessed it, 3/2 of the wavelength. 3/2 of the wavelength. All of which allows us to develop the wave string equation, which is very similar to the open tube equation. The main difference is that the wave speed is different than the speed of sound. This is no longer a sound wave, so this number is no longer 345. It's whatever the wave speed happens to be in that string. It's sometimes referred to as wave velocity, wave speed. This harmonic number still has to be a solid whole numbered integer. Going back to our string wave, suspended over a pulley system, with a force and a mass draped over the pulley, instituting a force of tension on this wave. There's a couple of equations we'd like to explore, and variables which can influence your wave pattern that's made in strings. The first equation we want to look at is this. The velocity of a wave is influenced directly by the force of tension of the string and the linear mass density of the string used. What's linear mass density? Here's the equation for linear mass density of string. Linear mass density is equal to the mass of a measured amount of string divided by the length of that same string. Because that mass is in kilograms, you can imagine string having very, very small numbers. And then in fact, dividing that small number by perhaps a larger number, meters, will make it even smaller. So linear mass density values are routinely really, really small, like in the thousandths place, which is totally fine. Force of tension we've already explored. Is it brought about by that force of gravity in the system? We also want to keep in mind that the wave speed or wave velocity doesn't exist in a vacuum, but rather interacts with our wavelength and frequency values. Let's say, for example, that we have a frequency or string vibrator set up to a set frequency value. So frequency must stay the same. And let's say that we begin oscillating this particular spring system with waves. But then we'll increase the force of gravity, thus increasing the force of tension. What sort of effect does that have on your wave? These are the sorts of questions that physics and College Board are trying to get at by giving us these two equations. Well, if force of tension goes up, then your velocity goes up. And if your velocity goes up and your frequency had to stay the same, then that means that your wavelength goes up. Other such direct relationships can be drawn in situations. Homework problems, quiz, and test questions typically having you solve for one variable and plugging it into other equations to find all other variables. These three equations work together and help describe what sort of waves are made in string systems.